Hello, welcome back. So in this new video, I'm gonna be explaining the code of a flip-flop. So we are going to be typing some code for the flip-flop type SCR, D, and T. So this is a Quartus software for programming the Max 10 FPGA, and let's begin. So first of all, the entity declaration. So as you remember, these codes will always need to declare the entity. So you will need to enter the inputs and the outputs. The inputs include the 50 MHz clock, the reset signal, and inputs for each type of flip-flop. So it will be the S, the R, the SR, the D, and the T. And now the outputs. So this will include various types like Q, QN, outputs for each type of flip-flop, as you can see. Now, the architecture. So we are using the architecture behavioral, and this case is for this code for the flip-flop. So it's defining the clock definer process like clock divider to generate a slower clock, clock new for faster clock, of 50 MHz, and the clock division is done by counting clock cycles. Each type of flip-flop, so will be the SR, the D, and the T, has its own process for handling inputs and generating outputs. So for example, if I want to simulate this, I will put in the alias like 2 for example, but if I want to check this code in the actual FPGA, I will need to raise the number like 25 so I can see how the LEDs are displaying. Now, let's jump for the SR flip-flop. So, its sensitivity to the rising edge of the clock new, depending on the input S and R, the output temp is 0 is set to accordingly. The output Q0 represents the Q output for the SR flip-flop, and the Q0N represents its complement. Now, the flip-flop D, it's sensitive to the rising edge of the clock new. The output temp is 1 directly set to the input D, and the output Q1 represents the Q output for the D flip-flop. Q1N represents its complement. Now, the flip-flop type T is sensitive to the rising edge of the clock new. Depending on the input T, the output temp 2 toggles. The output Q represents the Q output for the flip-flop Q2N, representing its complement. So now I'm gonna be jumping to the VHT. So this is auto-generated by Quartus Prime. So this is only for simulation processes. So this is the only part of the code that I changed. This block of code that it says begin in the variable declarations, the code that executes only once. So you can change these numbers for any number you want, but I put 0, 1, 2, 3, 4, 5, 6 until I get to the 15. So in each case, it will wait for 180 nanoseconds, as you can see. And that's it. So now, and also I add this part of the loop that is sets clock loop equals to loop, clock 50 MHz in 0, wait for 10 nanoseconds, clock 50 MHz in 1, wait for 10 nanoseconds, and to the loop. So this will be cycling in an infinite way from 0 to 1, from 1 to 0, as you can see. And it will be doing it forever. So it will execute for every event of the sensitivity list, as you can see. So now I'm gonna be jumping on the physical part. Thank you for stopping by.
Welcome back. Now we are in the physical part. As you remember, these are flip-flops. So we are using the type of D, S and T. So the first part is the T. So this is the switch 1. If I pull up this, these LEDs will be changing. So check this out. There's 1 second between each change, as you can see. Now, I'm gonna explain the second flip-flop. This is the type S, and this is the switch number 7. So 1, 2, 3, 4, 5, 6, 7. So this is it. Now, what happens if I pull this up? Nothing, because I have to reset first. This is the reset. It's already resetted. So now, if I pull up this, it will change, as you can see. But if I pull down the switch, it won't work. I need to reset this, as you can see. Now, I have to explain the flip-flop number type D. This is the switch number 4. So 1, 2, 3, 4. This is it. So this change once I pull up the switch, and it won't change after that. So it will stay like that. If I pull down this, it will be like the first step. So this is all for this video. I hope you learned something.